Welcome back to Module 3, ladies and gentlemen. Today we're going to talk a little bit off topic, I guess, but I think it's something that's really important. And we're going to talk a bit about statistics, and then we're going to move on to motor physiology. So we talked about the nervous system and how that controls flow of signals through the body, I guess. And we're going to talk about how that actually creates movement today. But we're going to start with an introduction to statistics. Two statistics is not easy to say. So we're going to talk a bit about mean, standard deviation, p-values, and some of the common statistical models that when you're doing your reading, and whether it's to do with the academy, for your assignments, or if you are interested in understanding some of the mechanisms behind some of the things that we will discuss throughout the course and look for papers on those. These things are kind of essential to look at, and I'm not going to overwhelm you with numbers or try and teach deeper maths, because I know a lot of people get put off by that instantly. But what I'm going to try and do is, in practical terms, show you what these terms mean, and hopefully then you'll be able to derive some form of meaning from the research papers that you look at, and be able to tell, at least on some part, what a good study is and what a bad study is, and some of the things that will influence those studies as well. So some things to look out for when you're doing your research. And then we're going to move on to motor physiology. So we've done nerve signal transmission, and then we're going to talk about that in relation to muscle movement. So that's quite a simple thing to talk through. I'm going to talk through sliding filament theory, a bit of a different take on that for you. I'm going to question some things and just make you think about some stuff that's more recent in the literature. And then basically we're going to go through muscle hypertrophy. So we're going to talk about a couple of mechanisms. There's some that are outlined in your module sort of text online, but there's a couple of things that I've added in this that I want to discuss as well. And then I want to just talk briefly about myofibrillar hypertrophy and sarcoplasmic hypertrophy, and where those philosophies come from and what the actual evidence is for them. Okay, so let's crack on with the introduction to statistics. I'm going to struggle to say that all the way through. Okay, so I'm just going to say stats now. So all statistics are based around some form of model. Okay, so if we're going to take two sets of data, if we're going to compare two sets of data, what we need is to be able to model all the numbers within those data sets. And the simplest model of that is our mean. Okay, so most statistical models, no matter what computer software you use, if you've ever done any statistics before, you'll find that the main model that people use and what they report in the literature is the mean. So that's just the average. Okay. And then with that, there's got to be some form of error, because as we'll discuss in a bit, and you'll see hopefully, the mean on itself, although it tells us some information, can be a bit misleading, because it takes a set of data, but it doesn't tell us anything about the variation within that data. And the variation, as you will come to see hopefully, is an important consideration. So what we'll generally do is we'll take a model with some form of error, and then we'll compare that to another model with some form of error for two different sets of data. Now these can be within the same people or different people. So we'll talk through an example in a minute, but what I want to go through first is just to talk about the most common parameters used in modeling numerical data, like I've just said, which is your mean and your standard deviation. Okay. So if we look at the mean equation there, so your n1 plus n2 plus n3 plus n4 and so on, basically means the number that you have for each participant. So if we look at the table on the right hand side, where I've got drug plus exercise weight loss, what I've done here is I've created a table for an imaginary drug, okay? And what we've decided to do is, in the development of this drug, this imaginary drug, we've figured out that exercise works synergistically with the drug. So the drug somehow triggers the body to use energy more efficiently. So something like carnitine is proposed to do. Okay, so what we found is, in our participants, we've got our 10 participants there. So the first participant, if we look down column A, lost 1 kilogram. The second participant lost 1. The third participant lost 1.5, and so on and so forth. So all we're going to do to calculate the mean is add all those numbers up together and then divide them by what would be NT on your thing, which is the total number. So that would be the 10 numbers added together divided by 10. And what we find when you add those up is that our mean is 2.75. Okay, so the average weight loss for our group was, or the mean weight loss was 2.75 kilograms. Okay, now if you ignore columns B, C, and D for now, we'll go through those in a second. So hopefully that's pretty straightforward. Most of us have calculated averages before, and like I say, they're not difficult to do, and there's, on Excel, which this spreadsheet is taken from, you can actually calculate the mean and actually the standard deviation from just using their pre-programmed routines. But I'm showing you how to calculate the standard deviation, so the next equation makes sense. So what we've got there, the standard deviation, is the square root of the sum of the mean minus the actual value squared divided by the number of participants minus 1. Now I know that sounds confusing, but we'll go through this now just to show you where that number comes from. Okay, so if we now look at the table again and we look on column B, okay, we can see we've got our x with a little line over it. All the way down that column is just 2.75 because that's our mean. Okay. Now in column C, what we've done is we're dealing with this minus x, x with a line over it minus x part of the equation. Okay. So all we're doing there is we're taking column B and we're subtracting column A. So if we look at the first line for the first participant, they have got 1.75. They have lost 1.75 kilos less than the average. Okay. If we go down to the 10 kilogram, you can see that they've lost 7.25 kilos more than the average there as well. So all we're doing is we're taking column B and we're subtracting column A from that. So we're just going to list all those all the way down there. Okay. Then what we're going to do to that number is we're going to square it. So if we go to column D, so we've got x with a line over it minus x squared. I couldn't do an uppercase proper squared symbol like you see on the actual equation that's noted on the left hand side there. So all we're going to do is square that number, and the reason we square that number is because we want to get positive values. Okay, so by squaring a negative number, if you go down and look at minus 0.25, you'll see that you get a positive number. Same with minus 1.25 in the next row, minus 7.25. And the reason we need that to be standardized is because when we look at a deviation, we actually note it as plus or minus. So we need to get everything in like terms because the variation applies to both sides of the mean. We'll come on to that in a second and you'll understand that a little bit more. Okay, so if we had minuses in there and then we add them up, that's going to really mess up our calculation because we can end up with, well, if we actually did that, you'd actually find if we just summated those things first, with not squaring them, you actually get 0. So obviously the variation isn't 0. So that's why we have to perform that function. So why we do it, I'm not entirely sure, but some clever mathematicians came up with this idea, and that's now the standard way to measure variation. So basically then, the sum of differences, which is your yellow highlighted square, is all those squared variations added together. So then if you look down the column there, so your 3.0625, 3.0625, 1.5625, 0.0625, and so on and so forth, right the way down, is then all just added together. And then in the orange square, which then relates to the bottom part of that equation, which is the segment under the n minus 1, all we're going to do is take that 74.125, okay, and we're going to divide that by n minus 1. Now n is just the number of participants, so as we can see in this, there's 10 participants, okay. So we're going to, n minus 1 is 9, so we take 74.125 and divide that by 9. And now we've got most of the equation sorted. It's just this big square root sign, okay, that goes over the whole equation on the left. So what we do then is we just take the square root of that, and we find that our standard deviation is 2.86. Now what's interesting about this, and you can see this from the data as well, is that our standard deviation is actually bigger than our mean, and that's not a good sign, okay, because that shows there's a lot of variety in the data. And with this simple set of data, what we can easily do is look at our initial data, so our column A data, and we can see that actually we've got one person who's had 10 kilograms of weight loss, and let's say this was over the period of a month, okay, this trial took place, so they had standardized exercise that we asked them to do, like burn a certain amount of calories, and then we give them this specific drug in a set dose. This person's had an exceptional amount of weight loss. Now, does that mean this person has done more exercise? Does it mean they've changed their diet? There's a lot of factors that could influence this. And as researchers, when we have data like this, what we have to do is we have to decide whether that person is representative of the data, whether the data is wrong because we've measured it wrong, or whether there's something else going on which actually makes it a valid piece of data, okay? So when there's a big variation, it can cause issues, and we'll talk about that why in a second. So hopefully, now you know what a mean is, and now we know what a standard deviation is, and those are the values that in most academic papers will be reported, okay? So if you've got two means that are quite similar, and there's a big variation, or even if the means are different and there's a big variation within the data around that mean, I would always be a little bit skeptical to make firm conclusions from that kind of data, okay? Hope that made sense. Let's go on to mean and standard deviation. Sorry, I covered the title a bit there, but I had to try and fit this all onto the screen. So if we look at the top left-hand diagram, our big thick black line going up through the middle is what would be our mean value, okay? So that's the size of the measure. And then what the graph going upwards, so on our y-axis would be, so x-axis is size of thing, our y-axis is the number of things. Basically, that tells us how many fall within that category as well. So if we look at our orange curve, that's a standard deviation of 0.5. Now you can see all the data is gravitated around that mean. Okay. The next curve, the standard deviation of 2, okay, is the red curve, and that shows you the distribution of the data is actually spaced quite far apart around the mean. Okay. And then standard deviation of 1 is somewhere in between those two. Okay. So we can see here that our means can stay the same, but the way our data is distributed can vary massively. So mean is a very restricted way of looking at data. And if we jump then put this into a practical example, so if we jump over to the top right-hand graph, okay, if we look at the number of people in the thousands is on the y-axis and the height in centimeters, so a really obvious one we can look at here. So our blue line is for men, and our purple line or pink line is for women. And we can see the means there, they're drawn on the graph. So the mean height for men would be around about 177.5 centimeters, I would guess. And for women around about 162.5, okay? And actually you can see with this kind of data that our distributions, our standard deviations, our variations are actually quite similar between groups. So we can probably say with some certainty, looking at the means and looking at the standard deviations, that the difference between groups is significant in terms of height, okay? And what's interesting, if you look at then at the sort of shaded purple area and the shaded blue area, you'll find that those are men, the shaded blue area are men with female height, and the shaded purple area are women with male height. So there's always some crossover. Now obviously if there was more variation within that, or maybe we took a population of an age, let's say when girls typically go through puberty slightly earlier than males. So if we looked at average height from men and women at the age of 12, what we might find is there's no significant difference, because what we've got to do is make sure our population is actually representative of what we're measuring, and making sure the distribution of data within that is actually representative of what we're trying to achieve. So to bring that back to our example, if we look at the table again, so I've just simplified the table now. So column A is exactly the same as the one that was on the last page. So we've got our participants down there, and we've got our mean and our standard deviation. Now obviously if we were looking at the effects of drugs plus exercise, that doesn't tell us much, because we're missing two things. One, we haven't got a control group, which is put in column C, that do none of the drug and none of the extra exercise, and they still don't change their diet or do anything, but they don't do any of that stuff. So if we start with C first and almost work backwards, you can see that our mean change in body mass is 0.175. So we wouldn't expect much change in weight. We wouldn't expect that change in weight, considering the fact that they're doing nothing different to what they would do normally, and our weight is maintained relatively stable for most people. And we can actually see then with the standard deviation of that, the variation is small as well. Okay, it's actually slightly bigger than the mean, but the mean is a small value, so we're not going to be too concerned about that. Right, now if you look at column A, like we said before, the standard deviation is actually bigger than the mean. So having said that, if we then think, well, okay, well, how can we pull out the interaction of the drug? We need to have a group with just exercise, okay? So they're still eating the same, they're still doing the same exercise as group A, but they're not taking the drug, because we need to be able to differentiate how effective this drug is on weight loss with exercise, because that's basically how we've decided the mechanism of this drug works. So if we look at the mean for that group, we actually find the mean is 1.43. Now if we were to just compare the three group means, so ignore the standard deviations for now, we see Group A has got a mean of 2.75 and Group B has got a mean of 1.43. So that's an extra, 1.3 kilograms of loss within that 4-week period over which the trial took place. So you might think, wow, that's really highly significant. Maybe this drug is amazing, and that's great, and the numbers do hold up to that. And obviously both those groups, A and B, have significantly more weight loss than the control group, which we would expect, because some form of exercise is going to create a calorie deficit on both those groups. So that's it. So we might conclude, just looking at the mean, that actually the drug works, and it works well. But like we've said, that doesn't account for the variation. So the variation, obviously, you said, is bigger than the mean, and the exercise itself, if we look at just exercise on its own, the variation is actually much smaller than the mean there as well. So we can say exercise is a fairly consistent way of doing things. And obviously, because we're doing these interventions, these are going to be different groups of people. Okay, it's going to be impossible to issue the drugs plus exercise to sort of both and just the exercise to the same people. So we're going to be using different participants in each of these groups to measure this. Now, these participants, they would typically in a study be matched for sort of age, their height, their gender, their activity level, their general nutritional intake. So there's a lot of factors that could be influencing these things. So instead of jumping to conclusions, because we've looked at that big variation, we might now think, well, hang on a second, yes, 1.3 kilograms of mean total fat loss for that group is impressive in terms of a difference. But because that variation is so big, we're now going to have to go and take a look back inside the data. And as we can see, there's that one person who's got that anomalous kind of 10 kilogram of weight loss within that month, okay? And obviously this is a made-up example, this isn't a real example. But then, like I say, what we have to do as researchers is be careful not to draw conclusions. Now, I've not run an ANOVA on this data. Now, an ANOVA is an analysis of variance, and I'll talk about that in a minute. And what an ANOVA does is it basically is a mathematical model, like we've just described, that compares the means and standard deviations of those three groups, and then it will tell us where those differences lie, okay? So a big variation doesn't mean something isn't going to be so significant. It just means that there's a chance it might not be, okay? So people cleverer than me have come up with these ways of mathematically modelling these things, but even within that, we need to be careful. So that's what we're going to move on to next. So just because a mean is different, we might find actually when we run this statistical analysis that there is no difference between the drug and the exercise and the actual just exercise group, okay? Simply because that variation needs to be factored into the model to compare those groups. So that's why scientific papers show a mean and standard deviation. That's why they're important, and that's why, you know, if you do start seeing this sort of data and they start jumping to too many conclusions and these big variations, always treat that with a little bit of hesitancy. That's not to say you shouldn't listen to it or take on board those points, but it's something that you should look for as well. So we're going to move on now to sample size, representativeness, and reliability. Okay. Now, sample size is basically the number of participants in a study. So, generally the bigger the better, okay? Now, there can be problems with this because, for example, let's say we're looking at this fat loss drug again, so same fat loss drug, and we take 1,000 sets of data, and consistently one group loses 0.01 kilograms, okay, over the course of the 4 weeks, but it's consistent between groups. So the drug plus exercise loses 0.01 kilograms more consistently than the just exercise group. So what we'll find if we run a statistical analysis on this with bigger numbers is that there is a statistically significant difference between those two. So we'll go, wow, this drug has an effect. But that's 0.01 kilograms per month of an effect. So when we run statistics, it doesn't care about the unit of measurement as such sometimes. So we need to be aware that just because something's statistically significant, it doesn't mean that something is physiologically significant. And this is something when drug companies are developing drugs that they're aware of. So they'll run these massive trials, but if the effect size, the size of the effect isn't actually, it might be significant difference, but if the effect size isn't measurable in terms of any physiological benefit, they're not going to run a drug or a supplement or so on and so forth, okay? Or any kind of intervention that they've designed. Obviously, most of the data we're talking about here is numerical data because fundamentally when we're talking about physiology, we're talking about quantitative data, so that's data that can be measured numerically as well. So there are other forms of statistical analysis where you can look at categorical data, but we're going to leave those alone simply because I don't want to get you bogged down in it, and quite honestly, the quantitative data is the best and gold standard way of measuring things, particularly things like randomized controlled trials, which I'll talk about again in a minute. So, yeah, sample size, the bigger and better. Obviously, the smaller the sample size, the less robust your research is. So, in the example we've drawn up before, we've only got 10 people. Like I say, if there's a lot of variation within people's weight loss, the bigger the sample size we have, the better the picture we're going to get, okay? So, there's this balance between having an excessive sample size, which just becomes unnecessary, and too small a sample size, where if I measure, for example, if I measure one person's height and go, well, that's the average height, that's obviously ridiculous. Same if I did 5, same if I did 10. If I measured 5 people from, say, a basketball team, you know, because they were convenient for me, that's not going to give a fair representativeness of the whole of the population. Okay, so that brings us on to the next point, representativeness. And that basically means how well do the group being assessed fit the overall population being assessed as well. Now, for example, in my research, I looked a lot at ACL injuries. So obviously, my group that I'm assessing have got to have an ACL injury. So, but how well do those ACL injuries represent the population I'm assessing? So, am I assessing ACL injuries in elite performance people? Am I assessing people with ACL injuries who are from the NHS or elderly populations? You know, I need to be aware of these things to then really get into the nitty-gritty of my data. So, an example of this within the bodybuilding world is when they look at the effects of some supplements on certain populations. Now, there might be a reason why it would work on those populations. So, if someone's got a vitamin deficiency, for example, vitamin D deficiency, then using vitamin D is obviously going to give them some physiological benefit. But does that then mean when you take that population and apply it to a healthy population who don't have any vitamin D deficiency, that there's going to be any benefit to those people? The likelihood is probably not. It may have some in some people, but in most people it won't, okay? So that's one thing to always look out for. When people quote studies and say, oh, this found this or this found that, look at what population they are and how that's actually related to the population you're talking about. So if you're talking about fat loss in obese people, is that different to somebody trying to get very lean for a bodybuilding contest? There are factors there that are at play, insulin sensitivity, so on and so forth. This comes a lot into the arguments of like low carb versus high carb diets. In certain populations, low carb diets work really well. In other populations, I personally think they're almost pointless. It's the calorie restriction that becomes the important factor. Again, we'll talk about that later on when we start talking about insulin and other hormones. So we need to be aware of that representativeness. So there needs to be a big enough sample size, and they need to be representative of the people that we're actually interested in. Now, that's not to say you can't transfer some data. So, for example, there's certain studies we won't be able to do in humans at this juncture. So if you've got animal studies, okay, always treat them with caution, but that doesn't mean we can't take lessons for them in very specific, basic sort of, I guess, physiological pathways. So I'm always skeptical with animal studies because human metabolism works differently, but on a very cellular level, there might be some of those things that are applicable, but that just comes with the experience of research. There's plenty of books out there on interpreting and evaluating research, so if this is something you're interested in, it's all out there. And the final thing as well is, a really important one is how accurate is the measurement tool. So let's talk about this body weight loss thing, right? So that with the example we've just come up with. Well, how accurate is body weight at measuring fat loss? What if I'm losing muscle tissue? Okay. What if I'm losing bone? What if this drug has caused some form of osteoporosis or some sort of proteolysis where I'm actually losing muscle tissue? So this comes down to the reliability of it. Okay. So what is the tool measuring actually what I want to measure? And how accurately is it measuring it? So if I was trying to measure fat loss, am I going to use weight? Am I going to use calipers? Or am I going to use one of these bod pod type things, which are very accurate? So you need to make sure when they're measuring something, it's actually measuring what it says it is. Okay. Classic example of this would be looking at the effects of protein on kidney function. So protein, because it breaks down into there's creatinine within that. Now, when creatinine goes high, it's usually a sign of kidney dysfunction. Okay, but unfortunately, high protein diets cause it, but it doesn't actually mean the kidney is in a state of bad health, as it were. So yes, the measurement is reliable, but the context in which it's used is inappropriate for people who have a high protein diet or who have creatine in their diet. So people who use creatine monohydrate, when it's broken down in the body, is converted to its unusable form, which is creatinine. Okay, so when we look at a measurement, we have to look at how reliable it is to actually measure what we're trying to measure. So, for example, just listing off examples, if we're trying to measure height and we've only got a meter ruler with no graduations on it, how accurately are we going to be able to measure that height, and how reliable is it? So reliability can come in two forms, really. So you've got basically how reliable is it between individuals. So if, let's say, there's two researchers performing a measurement, how reliable is my measurement going to be the same as somebody else's? Okay, so it's not just the measurement tool, it's how the person uses it. And most systems, even very sort of technological systems, there is an element of setup and things in it as well, so be aware of that. And the other one is how reliable am I? How repeatable are my measurements? So if I measure something today, am I going to measure it the same as tomorrow? If I'm trying to measure skin folds, how accurate am I going to be? And it's one of the reasons why skin fold measurement and caliper measurements, you should really go and do a proper course in those before you start using them, because the accuracy is good as long as the reliability is good, but the reliability for most people is actually very poor. Okay, so those are some things to look out for when you're looking at your assignment. So if you have a study that says, we found this amazing effect, but there's 5 people in it, state those effects as being, potentially there, but needs further investigation. Same with the representativeness. If we're looking at bodybuilders versus old age people, how well can we apply those groups? Same with the reliability. Are people inferring things from their measurement that they're not actually measuring? Okay, so that's a really important one as well. So we'll move on to p-values, because these are also listed as well. So p-value is actually, it's a measure of probability, but it's actually an arbitrary value. I don't know who it was, but some scientists got together and decided that a p-value of less than, so your p is less than 0.05, means there's a significant difference between groups. So a significant difference between groups means, at that level, means that there's a 95% chance that the results you found are because of the experimental effect, and there's a 5% chance found that it's not. There's a 5% chance that you found the result by accident. So basically, it means you're 95% certain that you've got it. But like I say, 95% certain still leaves some error. But if you've got a p of, say, you'll see these p-values listed. So it's usually listed as p is less than 0.05, as it turns as significant, but some studies will actually list the p-value. So a p-value might be 0.01, which shows you that it's very highly significant, because there's only a 1% chance that you got the result by error. Okay. Generally, what you'll find is if the p-value is greater than 0.05, it will be stated as there's no significant difference between the groups. Okay. Now, this can be dangerous as well, because obviously if you had a value of 0.06, it just means that, well, maybe you need further investigation. Maybe there is an effect there, but there's something else at play, so that we need to maybe change our groups, be more focused with our outcome measures, all this kind of thing. So what we tend to do, if any values that are sort of 0.05 to 0.1, we would say there's a trend. Okay, so when they say there's trends in data, what they're actually talking about is a non-significant trend. So yeah, we're not significant, but there seems to be something going on there that might warrant further investigation. Okay. So now you know what those two things mean. They're just basically an arbitrary value, and these are the results of these tests that I'm going to talk about now. So our t-test is comparing two groups. Again, it's the mean and standard deviation are inputted into these models. So we'd have, for example, in our example, we would compare our exercise group to our exercise and drug group. Okay, that would be a t-test. An ANOVA, analysis of variance, is comparing 3 or more groups. Okay, and that basically will tell you the differences between all those groups, and that's just like a multiple t-test. Okay. Now, when we're talking about these groups, with a t-test, you can actually have a sort of between participants or within participants as well. So we can have two groups doing different interventions, or we can have the same group doing the intervention twice, but with a washout period in between. And each of these comes with their strengths and weaknesses. So, for example, if we've got the same group of people doing the same thing twice, we know that their demographics are going to be the same. They're going to be the same age, height, weight, gender, so on and so forth. They're not going to change too much unless we're actually trying to do that kind of intervention. So in our case, in our example, that wouldn't work very well. But in, say, measuring the effects of certain foods on blood markers over the course of a week, yes, you could do that. And then in between that, you have a washout period where then you let everything go back to normal, and then you swap a diet or so on and so forth. So you've got the same people, which is a within groups, or you've got a between groups where you just go with your two separate groups of different people. Again, that's better because there's no learning effect, or there's no crossover effect as it's called, where one condition might influence another, but it does mean then that you've got to be careful for matching for age, gender, so on and so forth, activity level, depending on what you're doing. And an ANOVA is exactly the same, where you typically compare 3 or more groups. Okay, an ANOVA would typically be done between different groups. You wouldn't really expose people to 3 separate conditions. Simply, well, you can do that, but it's just very, very rare you will see that. Okay, so I'll move on to correlation now, and this is giving us an R value, and it shows the relationship between two variables, and this is typically within the same person. So an example would be, I guess, let's say high jump height versus long jump height. Okay, but correlation does not equal causation. So you'll say there's a correlation between one variable and another. A classic example of this is people who say, people who have high protein diets have more chance of chronic heart disease or so on and so forth. I'm just thinking of an example off the top of my head. And the reason for this isn't because of the protein as such, it's because people who have high protein diets, if we take ourselves outside of the athletic population, they will tend to have high calorie diets in general. So a correlation takes one variable from data and then tries to apply that. It's the same with a really good one that popped up the other day, is about alcohol and how a small amount of alcohol is good for you. Now, if we look at both ends of the spectrum of that, the people who will have a glass of wine every day, are they going to be the type of people who have a glass of wine once or twice a week, but then eat healthily and then exercise? And therefore their overall health is going to be better. And the people who either don't drink might just be people who can't afford to drink, but then have terrible lifestyles. They might spend their money on cigarettes, or they might not exercise because they can't afford leisure time, like proper gym time or anything like that. Or you could have the other end of the spectrum where you've got people who massively overdrink, and obviously that's not good for your health. So we look at all this data and we find there's a correlation that around about a few units of wine a week or alcohol a week is good for you, but in reality it's not the wine that's good for you, it's the lifestyle factors that consider it as well. So be very aware, there's a lot of people who will try and pull this as a kind of evidence-based thing, and it's just the one thing I will ask you to take home from this today is correlation does not equal causation, okay? Yes, it can give indicators. Yes, it can be useful in some situations, but for example, like I said with the high jump and the long jump example, one doesn't cause the other, does it? What causes the other is the fact that we've got stronger muscles, we've got stronger legs, maybe one person's taller than the other, so they've got a longer stride length, so when they jump, they can jump higher. You know, and then what we need to do then from those correlations is define more accurate measurements. So if we're going to form a hypothesis from those correlations, we're going to say, well, okay, is it leg strength? Is it leg length? We can measure those things more accurately, and then we can put those things into a model as well. So, and also as well, the other difficulty thing with correlation is something can have a significant correlation, but the effect of the actual thing we're measuring on that model might be small. So have a look at R values and what they mean, and in terms of what we can actually interpret that. So you can have a very significant correlation, but actually the effect of one variable on the other can still be very small. And a randomized controlled trial is the gold standard. Now these are very difficult to perform because basically they require complete control. So when you have these people with new drug developments, they'll take people away, they'll assign them to two groups. One will be a placebo, one will be the research drug group, for example. Neither will know what they're taking, and at the very highest level, even the researchers themselves won't know which group are assigned to which. So there'll be an independent person who comes in who does the allocation of the groups. There'll be an independent person who comes in and does the analysis of the groups. So nobody knows what's going on. It will only be at the end stage that the actual researchers get the data and then actually can do the data and the statistics and go through that stuff as well. RCTs are very difficult to perform in most settings as well. One, because they cost money, and two, because they're not actually applicable in all situations. For example, my research on ACLs, I couldn't do an RCT with that simply because the variation in terms of their treatment, in the variation in terms of their lifestyle, their rehabilitation protocols, they're too varied. There's too many things to control in a normal population, which makes on some level the value of my study relatively weak. But a good research paper will always discuss those things, and those things are called limitations, okay? So any good research paper will discuss its limitations. So if you ever want to read a full research paper, and this is why abstracts, reading just an abstract, which is normally if you go onto Google Scholar or PubMed or any of the kind of research journals, they'll give you an abstract. But yes, they're useful for getting a broad outline of something, but if you can actually get hold of a full text of a paper, it makes life a little bit easier, simply because you can actually go in and see if they acknowledge their limitations, and all good research will do that. So it's not about hiding those things and brushing them under the carpet. It's about acknowledging those things. So I think that's pretty much all we've dealt with statistics now. So hopefully you've got a good example, a good idea of what we were talking about. Hopefully that example's helped in terms of looking at some of the limitations of modelling and things like that. And now hopefully you've got at least the tools to go away and either do some further reading on it, or actually when you've got those research papers, be able to interpret those things a little bit better and have some idea of what they're talking about when they talk about these various terms. Okay, so let's get back on with some actual course content now. Okay, so we're going to move on to motor physiology now. So within the previous module video, we talked about how nerve cells transmit signals down them. So if we look at our top left image, we can see here we've got our motor neuron, and that's known as a Schwann cell in that case, because we can see it's got that myelin sheath around it as well. So remember, that's the one that has very fast nerve impulse transmission because it jumps across those nodes of Ranvier. Okay, and as we can see here, each motor neuron, if we go down and we start to look at their axons and their axon terminals, you can see that each nerve actually innervates or activates a number of different muscle fibers, okay? And that's how we get consistent movement, or coordinated movement, sorry, shall I say. Now the point between where these axon terminals are and the actual muscle fiber itself is called neuromuscular junction. Okay, so I'm going to just very quickly talk you through that. I mean, I've covered this in quite some depth within the module text online, but I'll just talk you through this very quickly to sort of give you a simple explanation of what happens. So if we actually look at the bottom right image now, you can see the different components of the cell there. So I've broken it down and trying to get as much information as I can into one image. So what's interesting about a muscle cell is if you look on the left-hand side list there, you can obviously see the motor neuron axon and the axon terminal, which I've described previously. The nucleus of a muscle cell is actually packed away to the outside, and that's because most of a muscle cell is actually this contractile tissue, okay? And then we have these things, so we'll just go down the left-hand side, T-tubule, and these are almost roots from the surface of the muscle fiber, deep inside to the on the muscle cell, deep inside to the fibers, to the contractile tissues, and I'll tell you why this is important in a short while. We then have the sarcoplasmic reticulum. Now this is a store of calcium. Calcium is really important for muscle contraction, and again, we'll talk about that in a great bit more depth. And then we've got our myofilament. Okay, so a myofilament is our actin, myosin, troponin, tropomyosin. It's got our structural backbones. These are contractile components there as well. And then we have our sarcolemma, which is just basically the outer component of muscle fiber. As we go along the bottom now, we've got a sarcomere, and a sarcomere is one functional unit of a muscle fiber. Okay, so it's from a Z line to a Z line, which then have their contractile components in it that cross bridge, and we have lengths of sarcomeres that run right the way along a muscle fiber, so from its origin to its insertion. Okay, so then obviously that encompasses the Z line. Your sarcoplasm is just your cytoplasm, so the fluid within a muscle fiber cell. So we're going to talk a little bit about sarcoplasmic hypertrophy, and also then the one above that, which is myofibril hypertrophy, okay, or myofibrillar hypertrophy. I don't know if myofibrillar is actually a word, but it's one that's used. Myofibril hypertrophy. Okay, we're going to talk about the merits of those. So as you can see from that end view there, that cross-sectional view, that a vast majority of our muscle fiber, or muscle cell as it were, is made up of these myofibrillar contractile proteins as well. And then also in there, obviously, on the top one there, we've got our mitochondrion. Okay, or mitochondria. That's the mitochondria is plural of mitochondria, which are our energy-producing power plants. So that's where we're going to talk about some modules about energy provision and about metabolic pathways. That's where energy is fundamentally produced. Okay, so we have our fatty acid oxidation going on within there as well. So the metabolism of fats and our carbohydrate metabolism as well. So let's just talk through quickly what happens then when a cell signal travels down on motor neuron axon. So as it goes down, it reaches the axon terminal, and within the axon terminal, there is then a release, as we well know, have already previously discovered, of a neurotransmitter. Now this neurotransmitter crosses the neuromuscular junction, and then it binds to receptors that are on the outside of the muscle cell. Okay, and this then allows sodium to transmit into it as well. Now these sodium-gated channels open down the T-tubule, and this electrical potential signal goes down the T-tubule until it reaches the sarcoplasmic reticulum. Okay, so it's basically turning an electrochemical signal from the transmitting an electrochemical signal from the axon terminal all the way through deep into the sort of the body of the muscle fiber. Okay, to get into this place called the sarcoplasmic reticulum. Now, the sarcoplasmic reticulum, like I said, is important because it contains a large amount of calcium. So why is the calcium important? Well, the calcium is important because it plays a very key part in what is known as sliding filament theory. I'm sure some of you will be familiar with this. So sliding filament theory is just the mechanism by which we turn that electrochemical energy into kinetic energy into movement, okay? So we're going to, and basically muscle contraction. So we're going to start on the left-hand side of the screen here, and we're going to just give a basic structure of an actin filament. Okay, so it's the binding of myosin to actin which causes movement. Okay, so under normal resting conditions, we can see that on that top left image in A, that our actin filament is actually, its binding sites are actually covered by tropomyosin. Okay, so tropomyosin covers the actin filament so that myosin cannot bind to it. On those tropomyosin sort of threads, there are these like beads of troponin, is a simple way of describing it, and they are manipulated by calcium. So if we move to the second image there, when calcium floods in, so when we've got this electrochemical signal coming down, potentiating through our T-tubules down into our sarcoplasmic reticulum, this stimulates the release of calcium, which then pulls the tropomyosin away, and this exposes the myosin binding sites, which then enables myosin to then bind to the actin to create movement. So how does it actually do this? So once the calcium is in place, binding sites are open, what happens? So if we move to the diagram in right now, we can see that in point number 1, the myosin heads split ATP and become energized, so they almost cock, okay? So if you can imagine they're sort of cocked forwards, they then cock like the hammer on a gun. Okay, so then we end up with ADP and a phosphate, so that first image right on the top there. Then we get a release of phosphate, and then that binds to the actin, and then it actually crawls and then uncocks, okay? So it pulls itself along. So it's called sliding filament theory. However, what actually happens is it sort of grabs and then it sort of pulls towards it. Okay, so we're sort of going down towards 2 now, so it's bound, and then in 3, the myosin head rotates towards the center of the sarcomere, so it's known as the power stroke, okay? So the way I would imagine this is if I was stood in a room, and I've got a rope attached to a wall at either side, or a bookcase at either side, and I want to pull those bookcases over, and I've got a rope in my hand, okay? So my arms are the myosin, and the ropes are the actin, so I'm going to grab that and I'm going to pull it, and I'm going to move my hands along, and I'm going to pull it again, and either way, these sliding bookcases are going to move towards me, okay? So, yeah, the myosin is the one that stays static and pulls on the actin, and pulls the actin filaments towards them, which causes contraction. In this example of the sort of sliding bookcases that I'm pulling, the bookcases themselves would be the Z lines, and then on the other side of them, there'd be somebody else with their ropes and their actin. So we get these lengths of these sarcomeres that are just, in series with each other, along each other, so that we can then pull and create a muscle contraction. Then what happens is once the energy has been released and the crawling movement takes place, the myosin heads then are re-energized with ATP, and then the cycle continues until calcium then leaves the cell. So calcium will leave the cell once it stopped being innervated by some kind of motor neuron signal. What's interesting about sliding filament theory is that it's actually far from complete. The idea's been around for a long time, and now we've finally got, micron, can't even say the word, spectroscopy. It was easy for me to say. We can actually look inside these things and see these proteins, but it's still very difficult to see how they work in reality. So there are some computer models that they've done, and actually what they've found with sliding filament theory is that it's almost incomplete. So they suspect that there's other proteins at play here, because the predictions from the models with the contractile force and stuff really is predicted quite well by sliding filament theory for concentric and isometric contractions, but it doesn't seem to add up for eccentric contractions when they do this fancy modeling. So they think that maybe there's another protein in there called titin, which acts almost as like a spring within it, so that stretches as the muscle sort of contracts, and then it actually adds to the force that you can produce eccentrically. It's not very well described in this because it's not very well described anywhere really, and it's something that I've only just recently read about myself. But if you want to look on a paper on this which gives a history of sliding filament theory, which is quite interesting about where the ideas came from and the past thoughts on what caused muscle movement or muscle contraction, is a paper by a guy called Herzog. It's Herzog, and that's in 2015. If you just type that in and sliding filament theory, I think it's a free text paper as well. So you should be able to download the whole PDF of that, so it's not just an abstract, so you can get hold of that as well. So now we know how we finally figured out how to produce movement from an electrochemical signal using calcium, manipulating these binding sites so that myosin can bind to the actin, and then we can create movement now as well. So we've just turned electrical energy, or we've turned our mind power into actual movement there. So that's how it takes place. So what we move on to now is just very quickly talk about what hypertrophy actually is. So we talk about hypertrophy, what are we talking about? We're talking specifically about muscle growth. And muscle growth can take place in two ways, really. We can talk about different types of hypertrophy. I don't know if I'll come on to that on the next slide, so I will stick with that. If not, I'll come back to it. And muscle growth is a net gain in muscle proteins, okay? So those contractile proteins that we see in there, the myofibrils, it's a net gain in protein, and it's called an accretion of protein within those muscles. And that's in relation to your net protein balance. So in this little equation we've got here, a very simple one, we've got NPB, which is your net protein balance, and that's equal to muscle protein synthesis, so the creation of proteins, minus muscle protein breakdown. So when we go on to the protein module, there's one of the nutrition modules about amino acids. We're going to talk a lot more about what influences muscle protein synthesis and muscle protein breakdown. Now, we might think then to get the biggest net protein balance, we want to have the highest amount of muscle protein synthesis and limit the amount of muscle protein breakdown. Now, that's true, obviously, because that's going to give us the most amount of muscle. However, there are things we need to consider with the muscle protein breakdown, as in muscle protein breakdown is also an essential process to actually remove old and damaged proteins. So when we talk about hypertrophy, we talk about We can talk about it in two terms, really. We can talk about it in terms of transient hypertrophy, which is just muscle pump, and we can also talk about it in terms of what's chronic hypertrophy, which is accumulated muscle growth over time that's consistent. Okay, they both play a role, and they're both outlined in your handbook. But two things I want to really talk about are the idea of myofibril hypertrophy and sarcoplasmic hypertrophy. Now, you can find these in quite a lot of even physiology textbooks, that these are stated as gospel. So myofibril hypertrophy is the growth of the contractile proteins, okay? So your actin, your myosin, they expand and they create more of those, which, widens the, which thickens the muscle cell, which creates growth. There's also this concept of sarcoplasmic hypertrophy, which is basically that it's growth of the muscle fiber cell independent of the myofibril hypertrophy. Okay, so it means that your sarcoplasm, your cell goo, as it were, your cell fluid is actually expanding as well. And the thought behind this originally stemmed from an idea that if you look at, say, a endurance runner versus a bodybuilder, or someone who's a powerlifter versus a bodybuilder would be a better example. They seem to have different muscle structures in the sense that bodybuilders seem to be fuller and rounder, but they don't seem to be as strong as powerlifters. But more recent research is starting to show that actually this is just more of the function of their training and their lifestyle than it is actually any difference in their muscle fiber structure as well. So that's why I've put a question mark on the sarcoplasmic hypertrophy, because we know myofibril hypertrophy takes place. That is a fact. We know that takes place. It's been demonstrated countless times. Sarcoplasmic hypertrophy has yet to ever be rated, okay, in any form. So, and particularly, I think the important thing is, obviously, as myofibrils are going to grow, then they're going to have to fill some space. The sarcoplasm is going to expand slightly as well. But from an evolutionary perspective, when we talk about the survival thing, it wouldn't make sense for a muscle to adapt to its sarcoplasm to have more fluid, because it doesn't actually add anything to the functionality of a cell. So we have to think about those things. The only things that might expand within the sarcoplasm are things like you would have maybe sort of fatty acid storage in there, and you would have glycogen in there as well. But when you actually look under a micron telescope on, I can't say that word today, micron telescope muscle cells, when you look at those things, you will actually find that that you can even barely see those granules of glycogen and those fatty acid globules, because they are so small. So when you're thinking about overall size increases, yes, the way we eat and the way we train can actually influence storage because of the energy system demands we place on our muscles. But in reality, if you want muscle growth, that's going to have to be led by the myofibrils, and then it might cause an adaptation in the energy producing stuff, simply because there is going to be more of a demand for energy with a bigger muscle fiber. It's why bigger people hold more glycogen. It's as simple as that, really. But the other way around, it doesn't seem to hold true, because there's no real evolutionary advantage to it, because muscles can only use fuel at a certain rate. So to have these big fuel stores when a muscle fiber can only use fuel at a certain rate becomes almost futile. So I'll talk a little bit about mechanisms of hypertrophy. So the top left one is a very old model. It's in your book. It's from Goldspink, I think, 1992. And that's explained quite clearly. So we have this rupturing of a Z disc caused by the oblique pull of the actin filaments. And then when that rupture takes place, then we have other proteins coming to repair that. We'll have increase in actin and myosin that then kind of fits into that gap that's then been created, and then we get an increase in muscle thickness. They seem to think this is one of the reasons why there's a limit on muscle growth, because the more those gaps fill in, the more oblique those pull are going to be. So if you think your tendons are relatively fixed, the thicker your muscle gets, the angle at which they can pull is going to be increased as well, which is why they think there's also a limit on muscle strength, because as the angle becomes more and more oblique, the pull becomes more and more oblique, you're actually losing effective strength because you're not pulling in a line of motion. So if we think back to that force component module that we talked about when we talked about lever arms, and we talked about the angle of the force application, this leads back into this because it actually works at a small level as well. So actually there comes a point where muscles get so big that the angle of pull actually becomes inefficient. So it's not that it's not useful. It's just that it doesn't have the same effect per muscle fiber size as a muscle pulling in, say, a more linear direction. I hope that makes sense anyway. Not important, not essential, but just an interesting little segue there. So what we found as well, and this is really interesting, is when people say that they have muscle memory, as things come back. There's a mechanism for this as well. So I've not put this into the module handbook yet, but it's something that I will put in future. So if we look at the image on the right, we have these things called myonuclei, okay? And what they are is they're satellite cell. Well, they're from satellite cells. So these are myonuclei are just muscle cell nucleus, and they're responsible for the creation of proteins, okay? So if we look at the image on our left and we look at the untrained person there, we can see they've got a normal amount of nuclei on the outside of their muscle cells, okay, the muscle fibers. But when we train, you get an increase in these satellite cells. So if we go first training route, we get an increase in these satellite cells. And then eventually over time we accrue these satellite cells that produce more proteins that allow muscle to produce quicker, okay? So we can actually recover quicker, but that makes sense. It doesn't mean we're going to grow faster, but the more muscle we have, obviously on a daily basis, we're going to turn over more protein. That's why we work out protein per day per gram, and it's not just a standardized amount as well. You need to take body size into the equation, or at least lean muscle tissue into the equation, simply because if you don't do that, you're not going to provide enough fuel to maintain that muscle. Okay, so it takes a lot more effort to maintain a muscle once it's bigger, which is why you have these increase in sort of myonuclei, so that you can make proteins quicker. So in one of the modules later on, we're going to talk a little bit in the hormone module. I'm going to talk a little bit about how proteins are created, and they take place within these sort of cell nuclei. Okay, so we're going to talk about that. But then what appears to happen? So if we follow our blue arrows, so we have our training session, we get a fusion or an increase in satellite cells. We create more proteins, assuming we've got the right nutritional stimulus as well. So then we have this trained person at the top of the image there. Then when it detrains, sorry, the arrow sort of fell off the edge of the screen there, but this is detraining going on. What happens when we detrain is we might lose, or we have poor nutritional status, for example, we might lose muscle size in terms of cross-sectional area. So you've got the previously trained person there, but what you'll notice between the previously trained and the untrained person is that those myonuclei, those cells, those protein producing cells are actually still there, so that when we start training again and we start applying the appropriate training stimulus and appropriate nutritional stimulus, we actually come back to getting muscle quicker, okay? So that's exactly one of the reasons why they think that people who've trained and they don't train for a while, they still maintain these protein producing segments of our muscle cells, so that actually we get back to where we were quicker. So that's one of the mechanisms which they explain muscle memory. Okay, so that's why guys who haven't been in the gym for 5 months can come back and be nearly back as strong and nearly back as big within a few weeks or months, compared to somebody who's just started training. I know obviously initially when you start training as well, you're going to get that proliferation of those cell nuclei a bit quicker as well. So the previously trained people will still tend to come back at someone who is quicker than someone who is actually relatively untrained as a starting point. Okay, so talked about types of hypertrophy briefly. So we've got transient hypertrophy, which is your short-term muscle pump. Obviously, it's still important because getting blood in the muscle is essential for delivering nutrients. There's a few things that can inhibit muscle pump. So if you're dieting for a contest, or you've not eaten well that day or for a few days, carbohydrates are obviously important as well, because nutrient flow needs to go and transport those things in. Fatty acids can actually play a role sometimes as well, but a big one for a lot of people is sodium. If you're struggling to get muscle pump, it suggests there might be a lack of salt in the diet, because as we've discovered before, sodium is really important to actually, it goes inside the contractile tissues and actually it pulls water into the muscle as well, which is going to allow you to get that fluid transfer nutrients, transfer growth factors as well. So that's why on a bodybuilding prep, for example, one of the things that people will try and do is actually manipulate, they'll manipulate their water obviously, because you want to be lean and dry looking, but you want that water inside of a muscle cell so you don't look flat. But if they can't get that water into a cell, it's either there's not enough carbohydrates in there, because carbohydrates will also pull water into a cell when it's stored, or it can be sodium as well, which can actually affect the uptake of carbohydrates. So one of the things I've seen done, which is like an advanced technique, it's not a lot of things people do. If you've got an experienced diet, you probably wouldn't need to do this, is when people are carbing up for a contest, they will actually regulate their blood glucose. And obviously if you're taking a lot of carbohydrates, that's fine, but if the carbohydrate levels, or your blood glucose levels aren't dropping, it means that the blood glucose isn't being transported into your muscle, because it's just sitting in your bloodstream. And then usually what would happen then is people will say, okay, well, the blood glucose levels are rising, they're not falling at any time soon, so what we need to do is put a little bit of salt in there to get the sodium in, to actually then shuttle those nutrients into the muscle. So that's an interesting take of something I've seen done. I don't know how effective it is in reality, but it seems to be used by some top-level coaches. And yeah, it seems to work pretty well for those people as well. So I'm not going to give someone's specific methods away. It's not Neil's. I read that somewhere else, so don't tell Neil. But yeah, these are different things that people try. But visually as well, you'll be able to tell that. I mean, someone like Neil, who's got that amount of experience, will be able to tell just looking at someone, having tracked their nutrient intake, having seen how they looked on refeed days during their contest prep. He'll be able to tell instantly pretty much what is missing from that equation to sort that out. Okay, so we have chronic hypertrophy, which is long-term muscle accretion. You'll see this word accretion used a lot in the literature, and basically that just means muscle growth. Okay, so the laying down of proteins. So muscle accretion means to grow more muscle. Simple as that. And then I've already discussed this previously. I don't know why I didn't wait till this slide. I always get excited and get ahead of myself when I talk about hypertrophy, because that's the kind of geeky person I am. So we've got an increase in myofibrils, and it's a proven source of muscle hypertrophy. Sarcoplasmic hypertrophy, you get an increase in volume of the sarcoplasm independent of myofibril growth, and at present there's no demonstrable evidence of that. Okay, so there's no evidence that sarcoplasmic hypertrophy takes place. And like I've said before, I explained some of the mechanisms why that wouldn't make any real sense anyway for it to do so. So maybe in the future there will be evidence of that, but at the moment there doesn't appear to be. And they've looked at athletes from all different kinds of sports with all different kinds of demands. And again, there always seems to be this fairly standardized ratio where most of your muscle cell is myofibrils, and then there's a bit of sarcoplasm around the outside with all your glycogen granules and so on and so forth, and the other little bits and pieces of the cell as well. So I think that's about it then for this, as is always noted by our nice white screen. So I'd like to thank you all for listening again. I know some of the topics I've gone over that are already in the literature, the online literature, but I like to do that simply because I think sometimes with the more complex topics, it's nice to actually have a different way of learning those things. So you can actually, you can listen to this on your phone or whatever, so that you can actually absorb that information a little bit better, or you can just listen to it aimlessly without having to spend hours reading, which can be tedious sometimes, I know. So one of the goals of this was to give different learning platforms. So I know I cover a lot of the same stuff again, but hopefully from talking I tend to get distracted a little bit and go off on these little, I'm going to say segue, I've started to become a bit obsessed with that word and I don't know why, but on these little meanders away from topic, which hopefully adds a little bit more detail and a little bit more depth to what we're talking about. So like I say again, thanks for listening, and you will hear from me very soon. Well, the next time you click play, if you're too keen, it could be in 2 minutes. Might be in a week. Anyway, happy learning. Bye-bye.